It's being recorded. Okay. So what have we done? We have done the following. If we have a commuting family of operators, commuting family of self-adjoint operators, okay, then we defined, let's see, we define sigma of x1 up to xn to be all those tuple lambda 1 up to lambda n in R power n. Such that there exists a xn with non-xn equals 1 and norm of xi minus lambda I xn equals to 0 as n equals to 1. Okay. So we took the collection of joint approximate eigen values of this family xi. Then we related, then we proved for any polynomial p small p in Tn. I mean, this is a polynomial which is which we treat as function on the sigma p of we can insert this x1 up to xn and we can get a operator which is a normal operator because x1 up to xn are self-adjoint operators, and this is a complex polynomial. So this is a normal operator. Then the spectrum of this sigma of this is equal to p of the sigma of x1 to xn. So we prove this. So as a corollary to this, this implies that this norm of this operator, this is operator norm, is equal to norm of this polynomial as a function in sigma. Okay. So this we prove. So we have the polynomial functional calculus. Polynomial functional calculus is just insert the variables, insert in the variable t1 up to tn, you insert the x1 up to xn, then you get an operator, which is just finite sum and finite product. So you get a well-defined operator. And the operator norm of that is the function, that is polynomial functional calculus. So you can define the polynomial functional calculus for any, for tuple x1 up to xn. Then that preserves the norm. I mean, the polynomial function, the norm of the polynomial as a function, the uniform norm of the polynomial is same as the norm of the operator. So this implies we get the corollary. There exists a unique homomorphism, unique isometric star homomorphism. I mean, even if I don't say, when we deal with C star algebras or any operator algebras, we consider only star homomorphism, which is unital also. Unital. Unital means it takes identity to identity. So whenever there is identity, it's unital, and it's star homomorphism. I mean, it may not, see, a homomorphism may not be unital. It may take identity to a projection. It's possible. I mean, you can always restrict to some subspace and you can do that. Okay. So, but we assume that it's unital. It's an important condition. Okay. There is a isometric unital star isomorphism by from this C of sigma t1 up to tn. So this is a continuous function in n variable. Okay. So it's a complex continuous, complex function, complex valued continuous function, to which you call it as pi, and which you do this b of h. But then this will be the C-star algebra generated by x1 up to xn, but I don't want to say it's into b of h. Okay, b of h, which we denote by f here going to f of x. We also call it as f of x1 up to xn. So the uniqueness satisfying f of so if you define this fi, this polynomial, fi of x1 up to xn equal to xi, where fi of t1 up to tn is just ti. Okay, we can take this polynomial. This is a single variable, 1-degree polynomial ti. So it takes that polynomial. I mean, it will take constant to constant because it takes identity to identity, and it will take this polynomial to this polynomial. Then such a thing is unique. Anyway, the proof is already there, but I am just stating it again. There exists a measure. There exists a measure. We will see it is unique later. Measure mu b of sigma. I mean, sigma is that sigma. So here it should be action. x1 up to x. B of sigma of x1 up to xn. There exists a measure mu on that, and a unique isometric, the same thing, isometric star homomorphism, isometric unital star homomorphism, pi tilde from L infinity mu of sigma into B of H. Again, such extending, I don't have to say that, extending pi. Okay. This also we denote by x going to f of x, but f can be measurable function, that's all. Okay. And the proof is already there. Proof, we have p of x1 to xn, norm of this is p, this norm restricted to sigma. So these polynomials, I mean, you can take the conjugate. These are all p1, p of t1 up to tn. The variables are real. And if you take the conjugate, only the, I mean, if f is there, the conjugate of the polynomial will be, you will get the coefficients, you will get a bar over the coefficient. Okay. So I'll just come on. Sorry. So this kind of polynomials, these polynomials are dense by Stone-Weierstrass theorem. Weierstrass theorem. These polynomials are dense, and it follows that by this p going to p of x1 up to xn extends a homomorphism on C of this. Okay. That is clear. Now we have already proved that if you have any compact set, I mean, it's not just for spectrum. If you have any compact set, if it has a representation on some p of h, then there exists a mu, I mean, which we defined through some process. There exists a mu such that you get a pi tilde, which is an extension of this. And such a thing is unique because you always have, I mean, the same thing is true. You always have continuous function, same argument. You have continuous function converging in measure to any measurable function, I mean, which is uniformly bounded. And the same thing, I mean, by the same token, by the same argument follows. Okay, the two also follows. It follows with the same argument. It's the same thing, except that we have to prove the uniqueness. But the uniqueness, we have the same. I mean, we proved some consequence of losing theorem that there, if you have some, I mean, if you have some measure space, if you have a compact metric space, then if you have a measure on that, then you can approximate any function in measure by continuous function. You can approximate again as almost everywhere also, almost everywhere, and then measure also. Okay. So it follows by these things. Okay.
Yeah, but we want to prove that for like subset of complex numbers, right?
Say it again. You want to prove?
Like we proved that, any representation of C of sigma extends, like when sigma is subset of complex numbers, right?
Correct. So we have real number. What's
C of
that?
sigma,
No, we just prove for
we have
compact.
Rn, right?
No, that proof goes through for any compact metric space, but it can be contained in complex number or real number. How does it matter? Real number is contained in complex number. What's the problem? Oh, here it is Rn. You are saying
Rn, yeah.
no. We didn't prove it for. We proved it for any compact metric space. We used complex number to define a function from complex number. It's a complex valued function. That's what we used. Just go through the proof. In any measure space, if you have any compact metric space and if you have a measure on that, then you can approximate it by continuous function. Any measurable function you can approximate by continuous function. Okay. To prove that the range is complex numbers, we defined a function on the range to do and used Lucian's theorem to do that. It's not for
So it works for any compact metric, right?
any compact metric space. Yeah. For a metric, any metric space is true. This is not just for any complex number. The same proof will go through. I mean, I might have said that we are using only for subset of complex number, but it's true for any compact matrix. Here we are using Rn. That's okay. It's just a compact matrix. We just need a compact Euclidean metric space. Okay, it will work. We used only in the range. If you go through the proof, we defined some phi on the range and composed it with any function. Okay, so the same proof goes through if it is, even if it is not a complex number. There's nothing special about complex numbers. Okay, so that's all. So now we want to prove something further. So this is for a finite family, a tuple of operators, a tuple of commuting operators, commuting self-adjoint operators. So that's what we have proved for a tuple of commuting operators. Now we want to prove the same thing. I mean, but the same thing will work for any normal operator. So now we want to prove the following: spectral theorem for normal operators. That's it. So if you have a normal operator, let T be a normal operator. Okay. Then T equal to some x plus Iy, where xn x comma y are self-adjoint, and x and y commutes, x, y equal to commutes. I mean, if any operator can be written as linear, I mean, x plus I, linear combination of self-adjoint operators like this. And if they commute, they are normal precisely when x and y commutes, which we have proved in the beginning of this course. Okay? So this is just, I mean, this is just a polynomial. Then now we also know that if lambda is also we know, if lambda is in spectrum of T, then and lambda equal to alpha plus I beta, then alpha is in the spectrum of X and beta is in the spectrum of Y. This also we know. So spectrum of T we can identify with sigma of xy. Is it like sigma of xy? No, it's not sigma. Yeah. No, it's not exactly like that. Correct. No, this is fine. This is fine. So if we have a lambda like this, and if there exists, I mean, lambda is like this is precisely that. What we proved is if you have a lambda equal to alpha plus I beta, if you have an approximate eigenvector for this lambda, then that is a joint eigenvector for alpha and beta. So that's what we proved. So this implies that sigma of T equal to, let me precisely write it, alpha plus I beta, where alpha beta is in sigma of x. Okay? This is what we proved. When we discuss normal operator, in the beginning of this course. This is what we prove. Okay, if you go through, if you go back and see, you will find this. Okay. So now we just know that. I mean, if you have the, if you take the polynomial just x plus iy, if you take the polynomial from sigma to c, which takes xy t1 t2 st going to s plus it. Okay, then this is a polynomial, and this normal operator is nothing but if you take this as p, then p of this xy equal to t. Okay, so it's clear. It's the same. So by these things we get. I mean, I have to write it again. So theorem. Except that I will write it in terms of see, and if you, I will write it and then explain. Okay, it will be clear. Okay, if, I mean, in the book there is something is explained, but I am saying in a slightly different way. That's all. So this is T be a normal operator. Okay. Then there exists T be a normal operator. There exists in one is continuous functional calculus. Continuous functional calculus for T. So there exists a unique homomorphism, star homomorphism, unital isometric, all that. Okay, isometric star homomorphism, f going to f of x. So this f is in C of sigma of t to f of t. So f of t, and this will be in C star algebra generated by t and 1. Okay. Satisfying satisfying the condition f naught of, let me define. I mean, we had an f naught earlier. It's the same f naught except that it's a complex polynomial. I mean, it's a polynomial defined on complex numbers. F naught of t equal to t, where f naught of z equal to z. One second. See, we have, so what do we have? We earlier had, instead of sigma, so let me just explain. We can identify sigma of t of t with sigma of xy by this alpha plus I beta going to alpha beta. It's a just, I mean, you can consider complex plane as R2 or something like this. Okay, you can identify this. Then you know that there is a continuous functional calculus from this capital sigma. I mean, taking x to f of x. Then it's the same f to f of x. But here you need, I mean, but when you consider complex polynomial, you have to make sure that the bar is also there. So here what happens is, if you have f0 z equal to z, it will also follow that if you take the polynomial f0 z going to z bar, which is also a polynomial. Okay, I mean, I mean, here the proof is it takes not just polynomials, it takes polynomials in z and z bar. Okay, the continuous function, whatever the polynomial functional calculus you have initially started with, that takes the polynomials in z. See here, both z and z bar are included in the capital sigma. When you make the statement about capital sigma, it takes care of both the polynomials in z and z bar. I mean, the polynomials in alpha beta or alpha minus beta, both are same. Both are okay. Both are same, right? I mean, no, it's not alpha and beta. You can take the, if you take one polynomial, then you can just take the bar in the, I mean, you will get only a minus sign when you use the z bar or something. Both the polynomials are included in when you take the talk about polynomials. But here you have to take the polynomials in z and z bar. Okay, but then that's also mapped to the corresponding thing, corresponding operators. So there is, I mean, this extends uniquely, and it's an isomorphism. Okay. If you have a problem, you tell me. There is really no problem. But Is there anything confusing here? I'm just saying you make a statement about, so when you have commuting operators and you got a functional calculus for the sigma of xy, which is in R2. Then you can make the same state. You can identify the sigma with the capital sigma of xy with this small sigma of t, the spectrum of t, as set. Then any polynomial here will be a polynomial here, except that it will be a polynomial in z and z bar. Okay. So that the Stone-Weierstrass theorem, you need z and z bar. I mean, for the Stone-Weierstrass theorem. So you can define the polynomial functional calculus on this dense subspace, which extends to the continuous functional calculus. Okay. The same thing is there exists mu and measurable functional calculus. Let me not say the whole thing. Measurable functional calculus. I forgot to say when I define measurable functional calculus, it is unique when it satisfies that convergence criterion. Where did I say this? Extending pi and satisfying convergence, I mean, which we know already, so I don't want to write it here, but anyway, I will write it there. Satisfying convergence. Okay, so I will write it here. There exists functional calculus and pi tilde, mu pi tilde from L infinity mu sigma of t to b of h, extending pi and satisfying the following. Satisfying, if you have a Fn contained in L infinity, norm Fn, supremum n is bounded, okay, and Fn converges to some f in measure mu, then pi tilde Fn converges to pi tilde f strongly. Okay. I'm just repeating the same thing again and again, except that now it's normal operator and all that. So what we did is we first proved the functional calculus, I mean, whatever the spectral mapping theorem for self-adjoint operators. Then we extended it to the family of commuting family of self-adjoint operators. A normal operator is in particular a commuting family of two commuting family of two for self-adjoint operators. And we applied to that when we got the spectral mapping theorem for any normal operator. Fine. So now let's prove the actual spectral theorem. If you have any doubt, you ask me now. If you have any doubt, you ask me now. I think the whole thing is clear now. Okay, this is clear, no? There is really nothing to worry about. Right? It's the same statement. It's fine. I don't hear any yes. Okay, I didn't hear properly, but it's okay.
Yeah, it is.
So if you have any doubt anywhere, you go through the book, you read it, or go through the notes. If you have any problem, you ask me. There is absolutely no problem because we have repeated the same thing again. Okay, now we want.
So the last statement is if and only if.
Which one?
Last.
What
Fn converges to f in measure.
Yeah.
Then.
Correct. It will be if and only if, right? If pi of Fn converges to pi of f, then Fn will converge to f. That also follows. I mean, that we have already proved for any C that is true. I mean, here this statement does not include that because this is we define a property and by that property, this pi tilde is uniquely determined. That is the statement here. So we are not saying if and only if or something, but the other way is also true. That's right. Which we have proved as a separate lemma or something, which is true. From that it will follow. Here the statement is the property which determines pi tilde. Pi tilde is an extension of this pi which satisfies this property. Okay, so that's why it's written. Okay. The other way is also true, you're right. Okay, but we are not mentioning it because that's not the property. I mean, that's not the. We want to mention the property which uniquely determines the representation. Okay. It's fine. Anyway, so this is the actual spectral theorem we want to prove. Before that, let us see what is spectral theorem, finite dimensional spectral theorem. Okay, what does finite dimensional spectral theorem says? Which we have seen already, which you have seen in your linear algebra course or something. So if T is a normal operator, is normal. What does it mean? Then there exists eigenvalues lambda 1 up to lambda n. Okay. So, and then each eigenvalue has an eigenspace, and there exist subspaces or projection. Let us call it projections. I mean, this eigenvalue can be one-dimensional, or it can be a. This is okay. If you, I mean, so T is an M and C. Let's call it K or something. I mean, this is, they are distinct up to, I mean, they are distinct eigenvalues. There exists distinct eigenvalues. If you count up to multiplicity, then they are one-dimensional. But I don't want to count up to multiplicity. I want to take the distinct eigenvalues, lambda 1 up to lambda k. Okay. Then there exists projections. There exists a family of projections. There exists projections p lambda 1 corresponding to p lambda k, right? Okay. And what does it mean? Then on the subspace, and then, I mean, on the subspace p lambda 1, this acts like scalars. That's what it means. I mean, if you up to a unitary, if you apply the, I mean, T looks like this, U of some diagonal operators, some diagonal operators, U star. But on these diagonal operators, it will be lambda 1 up to something here. I mean, whichever the number of times it will repeat. Okay. But then this P lambda is nothing but U of that 1 1 1 1 1, wherever 1 1 1, wherever that eigenvalue comes, and then 0 everywhere else. If suppose P looks like this, suppose T looks like, I mean, the spectral theorem says T will look like this. T will look like lambda 1, and then lambda 2, lambda I like this, and lambda I like this. Okay, then U star. Then P lambda I is nothing but U of 0 everywhere, and wherever lambda I number of times, if it is only one times, then you will get just 1. So wherever that lambda I comes, and 0 everywhere else is a diagonal operator, then you take U star. And since this is a projection, if you apply this conjugate with U, then you get a projection again. Okay. So those are those P lambda. Let me write the final statement. These are all just explanation. Let me write the final statement. The final statement is T exactly looks like this. So it acts like scalars on these eigenspaces. So it is basically this. T equal to summation I equal to 1 to k lambda I p lambda I. Right? That is how it looks like. Okay. So T looks like this. So corresponding to this lambda I, there exists a p lambda I. So you can actually say that, I mean, there is a map from this lambda 1 up to lambda n. There is a map p lambda 1 up to p lambda k, and this map uniquely, I mean, these are all projections. These are all projections in, I mean, this may be subset. Anyway, I'll just say projections. Okay, these are all projections. So in particular, if you want to define a measure on a finite set or even a countable set, then, I mean, this is the same thing. You can extend it for a compact operator, which we have already proved, except one lemma or something. We have proved the spectral theorem for compact operators. There you will get an infinite family, except then this lambda i's will go to 0. Okay, and there also you can write it as summation p lambda I p lambda. I mean, summation lambda I p lambda I. Okay, and now you have this finite set lambda 1 up to lambda n. This is exactly equal to sigma of t. Okay, and on this set, for each lambda I, you have a projection. Okay, then you take a subset of this lambda 1 up to lambda I, which is a finite set, and you have a corresponding lambda ik or something in there, and you can sum those projections. Since they are orthogonal projection, if you sum that will be again a projection. Okay, so you will get what is called a projection valued measure, which you can define on this. So that is precisely what we will have for a normal operator and infinite dimensional Hilbert space. Okay, that's what I'm going to do. So that's what I have here. So I will write one by one. I will not write the whole proposition. I will recall each and every property and then prove it. Okay, so the spectral theorem is the following. So if we have an operator, so the screen has come now, so it's there. So yeah, so this T be a normal operator on a separable Hilbert space H, then there exists a unique spectral measure. So it's a measure, but except that it's not a positive measure or something. It's a measure which takes values in the space of projections. Okay, it's a, and what we mean by is the following: for each E, for each subset E, each Borel set. I mean, here I'm defining on, here it's defined on the whole complex number, but the measure will be concentrated on the spectrum. That's the final statement we are coming. Okay, it is just you are taking the intersection with the, you are taking the intersection of the set with the spectrum, and the spectral measure is actually defined on the spectrum of T. Okay, so P of E is a projection for all E. For each E, it's a projection. And if you have ENs, if you have disjoint projection, I mean, which is not clearly said, but it will be clear. I mean, sum of two projection is again a projection if and only if they are orthogonal. Okay, otherwise it's not a projection. So because of that, it will follow. Okay, if you take two disjoint subset E and F, E intersection F is empty, then the projection corresponding to E, projection corresponding to F are orthogonal, mutually orthogonal. Okay, they are orthogonal subspaces. That will follow from this. But the statement here is, if you take some family En, where En is a disjoint family, this is the definition of measure. Okay? En intersection Em is empty. Then you talk about E, which is the, I mean, union of all this En, disjoint union of En. Then P of E equal to summation N in P of En. But here they are all projections. So you have to specify what convergence is this. And always for projection, you cannot take norm convergence. You have to take strong topology. So the convergence isn't a strong topology. So if you take a disjoint family of sets, disjoint family of Borel sets, then the projection corresponding to the union is the sum of the projections. Okay, since they are all orthogonal projection, the sum will also be projection. I don't know whether you know this exercise, but maybe I will give an exercise here. Exercise. Maybe for finitely many, it's infinite many also you can write. Summation Pn, projection, if and only if Pn is orthogonal to Pn, for all n not equal to n. Okay? Maybe I'll write it. Exercise. Summation Pn, the summation is in strong topology always, okay, is a projection. Is equivalent to saying Pn is orthogonal to Pn. The subspace corresponding to Pn is orthogonal to Pn, or you can say Pn equal to Pm equals 0. They commute and their product is 0. Pn is orthogonal to Pn for n. Okay. So because of this projection P of E is a well-defined projection. So you have got a projection valued measure. Okay, you can take measure in complex number, you can take a measure in Banach space, you can take a measure in anywhere where you can add things, wherever you can add, and you have a topology. You have to define. I mean, you have to take a countably many disjoint sets, and then you have to define the sum. So for that you need the topology, and you have to add. So it has to be a kind of vector space. Addition should be defined. That's all. Then wherever you can define that, you can define a measure. Okay. So this is just a projection valued measure. The spectral measure is a projection valued measure. Okay. Then the spectra, then it satisfies several properties, which I will list. Okay. So first, let us get the projection. Spectral theorem. So we have this. We have functional calculus. So T is normal. Is normal. Okay. And the screen has come here. So T is normal. Then we have functional calculus. F in L infinity mu. I mean, we have a mu, still some mysterious mu is there. That mu is not well defined. You'll see that mu is, I mean, we will get the mu, concrete mu after this. Okay, after the proof of spectral theory. Okay, L infinity mu f going to this f of x in B of h. Okay. In particular, you define P of E equal to 1e of this. Here it is t. So I was using x earlier, but it's normal, so I'm using t. 1e of t. Okay. Is a projection. We know that this is a projection we have already seen. This is spectral projection. This we can define for any e in any e contain any e is in BC. Okay. By taking the intersection, I mean, if you make E intersection sigma t, you can take. Okay. You can define PE like this. This is just the spectral projection. Okay. You can define PE. And then it is clear if En equal to E, if we have a disjoint union like this, then this this n, I mean k equal to 1 to n, ek, okay, increases to E, right? As sets. Okay. So this implies 1 of union of k equal to 1 to n, ek. This function, this converges to 1e. I mean, almost everywhere, or mu or whatever. It's a convergence in measure is enough, but it converges in almost everywhere. It converges pointwise. Okay. Always everywhere. So this implies p of that whatever p of en, but this is equal to summation 1 ek. K equal to 1. Okay. So p of, so if you apply the functional calculus, it just implies summation p of ek k equal to 1 to n converges to E strongly as n goes to. Okay. So it's clear. The same proof. Okay. So our functional calculus is calculus gives rise to the spectral measure. Okay.
Converges to PE.
Yes. What did I write? Converges to PE, correct. We write E. Okay. Yeah, it converges to PE. Okay. The second thing is, so this is clear. Okay, it's a spectral. I mean, it's a spectral measure. You get a spectral measure just taking the spectral projection, and it's a projection valued measure where the convergence is in strong topology. Okay. Now we want to define. We want to get a finite measure. So this is second. For all x in H, okay, you define this Pxx. Pxx. This is a mesh. Pxx of E equal to P of E. P of E is a projection, xx. Since P of E is a projection, this is also same as P of E x norm square. I mean, you can write P square here, and then you can take it to the other side of the inner product, and then you can write it like this. Okay, it's a finite measure. It's a finite positive measure. It's a genuine measure. Okay? It's not a complex measure or something. And it's clear. I mean, if En increases to E, okay, then P of En converges to P of E strongly. Okay. Then the P of Enx will converges to P of Ex, and then the inner product will converge. So it's clear. Okay. The statement is clear. So you get a finite measure. And Pxx of the whole complex number. Notice that if you have the whole complex number, then the P of the complex number is 1 because it's unitary. Okay. P of sigma of t is 1. P of sigma of t equal to 1. Right? It is just, I mean, that's the whole set, and it's the identity function. It's a constant function 1, and that will go to the identity operator here. So B of xx equal to identity operator. That is equal to norm x square. I mean, this Pxx subscript xx is a measure. I mean, when you have the spectral measure P, which I am calling it as P, then I write this subscript xx, and that you get by this inner product. Okay, and that is a finite positive measure. That's what I'm saying. So that's clear. And the third statement, for all xy in H, okay, pxy, you can define pxy. You can take x and y, you can write take p of e x comma y, okay, for all e in Borel set, for any Borel set in BC, is a complex measure. Okay, is a complex measure satisfying. Of course, that finite measure, finite positive measure, is just a special case of this complex measure, satisfying. So if you have a complex measure, you can integrate with respect to complex measure. I think we did that, right? Okay, you can integrate with respect to complex measure. If you want, I mean, you can take simple function and sum, and then you can do that. You can integrate with respect to spectral measure also, okay, directly with the spectral measure, or you can integrate with respect to this kind of complex measure that will determine an operator, because all this inner product will determine an operator, no? So because of that, the operator is uniquely determined, and or you can even take the quadratic form, this PEXX. That itself will determine an operator. I mean, that's for self-adjoint operator. But the okay, you can take the XY and that will determine the operator. Okay. Okay. Satisfying the following. Satisfying what? So I didn't say what it is. Satisfying the following. So if you have a function f for all satisfying for all f in L infinity mu, or if you wish, I mean, the mu is there, mysterious mu is there, or you can take the continuous function itself if you want. Continuous function is enough to determine the operator, but I'm saying that whatever the mu is in the background, you can use that also. For all f in L infinity mu, integral of this is a statement. If you have f, then you can talk about f of t. Okay, then you take this integral, then you take the inner product, and that is exactly equal to f of z. Right, z is in the complex number. Then d p xy. This is a complex measure. Okay, fine. This is actually over complex number, but you can just take it to be sigma t. Sigma t are complex number because it's outside. Measure is 0 outside the sigma t. Okay, you can write it. So this is precisely the spectral measure. This is spectral theory. As you can see, R, or in other words, f of t, this operator f of t, you can write it as integral over h, integral over sigma t f of z dp. Okay, dp is the spectral measure. You can integrate with respect to, I mean, I don't want to go into that. This integral is defined through strong topology. See, what is an integral? Integral is a generalization of summation. Okay, but then you are taking limits. Whenever you are taking limits, you have to define the topology. Here, the topology is strong topology. You can define this integral for simple function just by summing. You don't need topology for that. But then every measurable function can be approximated by simple function. So then you can define the integral for all those functions, which you can just take the closure of the simple functions wherever it converges, almost everywhere, or in measure or whatever. You can define for all those functions. Okay, all those functions, any measurable function, you can write it like this. You can define the integral. Okay? I mean, this is not. There is something called Bochner integral. It's not that. Because this is in strong topology, this is something different. And but if you don't have to worry about this, the meaning of this is precisely this, right? But any operator is determined by this form, no? This inner product. If you have an f of t equal to xy equal to this, then this f of t is defined. So any operator which satisfies this. In particular, you can get the operator. In particular, t equal to integral f of z. Sorry, no, just the function z dp, where the integral is in sigma. or t xy. Any t is determined by this inner product t xy equal to over this. You have a complex measure on this, okay, and you can write it dp xy. You get a complex measure. You get a complex measure pxy, and you integrate with respect to that complex measure. Okay, you integrate with respect to the complex measure. The function z, okay, the z going to z, the identity polynomial. Then you get the operator. Get back the operator. So you have this, you know the spectrum, and you know the spectral measure. Then you get the operator. This is precisely the spectral theorem. So let me just prove this. We haven't proved it. Proof of 3. So we have to prove this. We have to prove this star. Okay. Where star is, you take the inner. So for any t, you can define the operator f of t. Okay. That is defined through the measurable functional calculus. On the other hand, you have the spectral projections, and using those spectral projection, you got this measure pxy, which is the complex measure. Okay. Then if you integrate that function with respect to that complex measure, you have the measurable functional calculus, and you take the inner product, and these two things are same. That's the claim of this. You have to prove this. Okay. Okay. So how do we prove it? First thing is, notice that. So I am calling this statement a star. Okay. Notice star is valid for simple functions. Right? What does star say? Simple function means, simple function is sum of projections. Okay. And if it, so these are all both sides, it's linear in F. You can sum F1 plus F2 here also. If it will be integral is also linear, inner product is also linear. So you can, so it's if you take any one E, if you take any spectral projection PE, there is really nothing, there is no really statement for simple function. It's the same statement. It just says PE of xy. You will get PE, the integral, you will get, simple function for a, it is enough to check for indicator function for f equal to 1e, for example, f equal to 1e, integral 1e of xy, okay, which is just equal to PE of xy. That's what we defined it. And this is precisely equal to PE of xy. This is equal to pxy of e. That is how we defined this complex measure. And that is precisely the integral over e of this f. F is the indicator function. If you wish, you can write 1e if you wish. 1e of dpxy. This is precisely the definition of the integral. Okay. So it is satisfied for any simple functions. So now for f in L infinity. So f is in L infinity, then we have simple function for any bounded function. For any bounded measurable function, we have simple function converging uniformly. That's what we proved. First thing proved in the measure theory class is that. When we discussed integration, the first thing we proved is that. So there exists simple function. There exists a simple function such that it is uniform, means it's in you can approximate in the L infinity now. There exists simple function S such that norm of S minus F, the infinity norm, L infinity norm, is less than epsilon. Okay. So now for any F and epsilon greater than 0, given any epsilon greater than 0, you can find a simple function such that S minus F, L infinity norm, is less than this. Correct? Okay. Now this implies the functional calculus preserves the norm. So this implies S of t minus F of t is less than epsilon. Correct? Is that right? Am I missing something? No, we want to prove this is okay, no?
Yes, sir.
This is okay, no?
Okay, sir.
Missing something.
Yeah, it's fine.
It's fine. So we can always approximate in L infinity now. Correct. This is okay. Yeah, this is okay. Okay. On the other hand, yeah, this is okay. On the other hand, let us talk about this norm of this. So this is the L infinity norm. So the operator also satisfies these things. On the other hand, integral of S dp xy minus integral of f dp xy, this mod, is this is equal to integral of s minus f dp xy, which is less than or equal to integral mod s minus f dp xy. This is less than or equal to epsilon times, this is less than epsilon times this pxy of the whole set. Okay, sigma of t or c, whatever. Okay. I mean, which is what is called the mu of, I mean, which is the norm of, I mean, if you have a complex measure, then the measure of the whole set, measure of the total variation of the whole set. So this is less than or equal to, I mean, this is the complex measure. No? So you can have the, what I mean to say is, you can replace it by d, the mod complex measure, right? Which is the positive measure, right? You can replace it by that. So this is equal to mod of mod tf dxy of c. Fine. It's fine. This is okay. I'm just taking the integral with respect to the complex measure. Then I am taking it inside and then I have written it like this. Then you are integrating with respect to complex measure of anything that is less than the integral with respect to, I mean, the integral of the, maybe I will come one day. So I am integrating with respect to complex measure. That's right. So integrating with respect to complex measure. So they are not finite measures. So I am just talking about the difference between them. Is equal to the mod of integral s minus f dp xy. I want to say that this is less than or equal to, I mean, this is clear by this representation theorem. See, the point is, if you have a complex measure, then that gives a linear functionals on continuous functions. Then you can extend that linear functional to L infinity. It should be direct. No? So this is less than or equal to, all I want to say that this is less than or equal to norm s minus f, the L infinity norm, which is less to epsilon times norm of px. It is clear to me. I'm just trying to see how to say this. Because we proved Rees representation theorem for positive measures. We didn't prove it for complex measures. If you have any complex measure, see, if you have any, we proved that any positive linear functional on C of x is given by a positive measure. But if you have any complex linear functional, any linear functional, bounded linear functional, that is actually given by a complex measure. In fact, but then you need to work a little bit. But the converse is clear. If you have any complex measure, then that complex measure can be in some way uniquely written as finite linear combination of positive measures. So it's a linear combination of positive functionals. See, when we proved the total variation measure, the total variation measure, see, any complex measure can be written as linear combination of positive measures. And the total variation measure is just the sum of those positive measures. If you have digression, if you have a mu be a complex measure, I don't know what decomposing is there. Mu can be written as mu1 plus mu1 minus mu2 plus I into mu3 minus mu4. And this is actually unique. I don't remember the name of the decomposition. And this mod mu of the whole set x is a complex measure on x or something. Then whole set x is equal to mu1 plus mu2 plus mu3 plus mu4 times of x. Is that right? Or it is the square of that? No. For signed measure, it is a sum. For complex measure, it's not the sum, I think. It is just the modulus. Yeah, but in any case, this is true. Okay. If you have any complex measure that has a real part and imaginary part, and they are the signed measure, okay, so you can write this sum as, you can write this integration with respect to the real part and imaginary part. And the real part of that is just the difference of two positive measures, okay? And the total variation measure of that signed measure is mu1 plus mu2 of the sum of those positive measures. That is some, I don't know which decomposition is that. It is in Sundar's book also is there. It's a unique decomposition which will give that. Okay. And from that, this follows. Shall I see if it is clear? If you say it's clear to you, then I will just stop. If it is not clear, then I have to give more and more explanation. This is very clear. Okay. I'm just saying that if you integrate a function, f with respect to d mu, which is a complex measure, then this mod of this is less than or equal to norm f, the L infinity norm of this times this mu of this whole set. Okay? So this is something, and I will leave it as an exercise, and it's clear to me. Okay. If you don't find it, you tell me. Okay, this is easy. Okay, if you work it out, you will get. Okay, so I leave it as an exercise. Okay. So now because of that, this is equal to epsilon times this norm of pxy. Right. So this integral is the integral difference is less than some. Sorry, here this is epsilon. So the integral difference is epsilon times something, and then this difference, whatever the other difference, what is the other difference? The norm difference is also less than epsilon. So in particular, if you write st, s of t minus f of t xy, this mod, or I mean, this this mod is less than epsilon times norm x norm y. Okay. I mean, because this norm of this is less than epsilon, that's what we have here. And because of that, this is true. So now notice that s of t coincide with the integral. Okay. And s of t minus this is less than epsilon times something. And the integral of s with respect to dpxy is minus this is less than epsilon times something. Okay. So this implies f of t, this mod of f of t minus integral of f of z dp xy z. This mod is less than epsilon times norm x norm y plus epsilon times pxy. Okay. But all these xy, all these things are fixed. So this is true for all epsilon. So this implies f of pxy is equal to integral of z. Is clear? I mean, this integral representation holds for simple functions, and then any function can be approximated by simple function. So this is true for any function, any measurable function. Okay. I think I have spent a lot of time on this. Okay. So let's go to the final one. What is the last statement? Fifth statement is support. So whatever that mu we have, mu is the measure. There is a measure mu in the background, which is still not clear what the measure. We just know the measure exists. Okay, mu is supported in sigma t. Means that is sigma t. I mean, the support of a measure is the smallest closed set. So, or I will just write it. Definition: support of mu, any measure mu, equal to the smallest closed subset uh, outside which whose complement is zero measure, okay, which is equal to intersection of all f such that all f closed such that f complement mu of f complement is zero. Should write f here. Integral for all f closed and mu of f complement is zero. Okay. It is the smallest closed subset. I mean, the support is in topological space. I mean, in the metric space also. So this is the smallest closed subset whose complement has measured zero. Okay. So mu has support sigma t. Sigma t is a closed set. So we have to prove that the measure is supported. I mean, supported means you don't have a small, if you have any closed subset which is strictly contained in sigma t, that cannot have the full measure. The complement will not have the full measure. So all we have to prove is, so this is equivalent to saying the other statement. This statement is equivalent to saying for all open u such that u intersection sigma t is not equal to empty, that mu of u is strictly greater than 0, which we have actually proved. If we have any, but we proved for self-adjoint. So here we will prove for this also. It's the same thing. The proof is same. We proved for self-adjoint. If you have any T naught in the spectrum, then you take the epsilon neighborhood around that. Okay, that will be contained in any some open set. There will always exist epsilon neighborhood, and that has measure not equal to 0. Oh, sorry, this is okay. Oh, I forgot. This is not mu. This is p. I'm sorry. And we have mu and p has a relationship, same relationship. Mu is also supported, but the statement here is about p. Okay, so p is supported. P is supported. Mu of p of. I mean, you can talk about zero projection anyway. So p of f complement is 0. Okay, talk about zero projection. such that for all open U, P of U is not equal to 0. Not equal to 0. Or the subspace corresponding to this P of U is not trivial, which we have already proved for self-adjoint operator. If you take any T naught in the spectrum, then you take any open neighborhood around the spectrum, not any epsilon neighborhood around the spectrum, then the spectral projection corresponding to that is not trivial, which we proved in the 2-3 classes before. Okay, so this is precisely that for this. That's what we want to do. Okay, proof. But here it's complex. This is in the complex plane or something. Let's Z naught is in U. Okay, and we want to prove that suppose. So we want to prove that if U intersects with sigma t, then it is then it's not equal to 0. So to prove the other way, we have a U which has measure 0, then it does not intersect with sigma t. That's what we want to say. Okay. So let's take an Z naught in U. Okay. So suppose we prove the other way. Not the other way, I mean negation of the statement. Opposite of the statement, not negation. Suppose U intersection sigma t is empty. We want to prove no, P of U equals 0. Suppose P of U equals 0, then we want to prove. That's what we want to prove. No? We want to prove U intersection sigma t is empty. Right? This is what we want to prove. Okay. So suppose Z naught is in U, there exists epsilon greater than 0, such that all those Z, such that mod Z naught minus epsilon, this disk, open disk, less than epsilon, contained in U. Okay, we have contained this. So not epsilon here, this is Z. Okay. Because it's open. Okay. Now P of U equals 0. So in particular, you this then P of this set Z such that Z minus Z less than epsilon is also equal to 0. But then this implies that the function, whatever this function we have, this Z minus Z naught, I mean this function F naught dz equal to is invertible. I mean, we can talk about one minus. I mean, measure of this set is 0. So 1 by Z minus Z naught. Okay. This function 1 minus Z minus Z naught is this Z going to this function. Sorry, not F. Z. This function is in L infinity of U because of this, right? This we have seen earlier. I mean, if you want to define continuous function invertible, then the function should never vanish. But for L infinity function to be invertible, this is the condition. There should exist an epsilon such that Z naught minus Z less than epsilon. That set should have measure 0. Okay. Right? This is an L infinity mu. I mean, I just this function is L infinity mu. So this function, this just says that this function F naught minus Z naught is invertible in L infinity, where F naught of Z equal to Z. Am I confusing here? This function, say, let us call this as D equal to this. Okay. Let me come down. Because I'm confusing with mu and D, so there may be a problem. So let us argue it correctly. This is P of D equals 0. Okay. This means 1D equals 0. 1D P of D equals 0, 1D of T equals 0 as an operator. That's what it means, right? P of D is just 1D of T by definition. That is equal to 0. So this implies 1D as a function is equal to 0 as a function in L infinity. Equals 0 as function in L infinity. Okay. This just implies mu of D equals 0. Okay. This implies 1 by Z minus Z naught is in L infinity. Okay. This implies 1 minus F naught minus Z is invertible in L infinity, where F naught Z equal to Z. This implies, sorry, not 1 by F naught, F naught minus Z. F naught minus Z. This implies, if you use the measurable functional calculus, T minus Z naught is invertible. This implies Z naught is not in sigma of T. That's what we want to prove. Okay, I'm sorry if I had confused, but the proof is clear now. The final thing is sixth or something. Spectral measure is unique. That is because the spectral measure, I mean, what do you have? So spectral measure is determined by the, so you want to prove the spectral measure is unique. It's enough to prove spectral measure is the P of, I mean, E going to P of E, okay? Which is a, spectral measure is E going to P of E. But then it is enough to prove, if suppose if you have two spectral measure, it is enough to prove this is uniquely determined. Of course, any such, this form uniquely determines any operator. In particular, all this P of E will be uniquely determined. Okay. So suppose if we have two projection, suppose we have two spectral measure in the sense that we have two spectral measure with respect to which the operator is determined. Okay. So the operator is determined. Okay. So E equal to P of E, we have Q such that integral f of z dp equal to integral f of z dq. Okay, then p equal to q. That's what we want to say. Okay, enough to prove p of e xy is equal to. You want to prove p equal to q, which is equal to q of e xy. Okay, but then this is, I mean, you can take see the, I mean, this is equal to, for same operator, this is equal to f of t. This is equal to f of t, right? This is equal to f of t. Okay. So let f be any, you can take polynomials in, and this will anyway give a continuous function on the, no, this is 1 to 5. That is uniqueness. There is no statement about uniqueness. Given an operator, there exists a unique spectral measure. This is just clear. No? If you have any continuous function, the complex measure, see, if the integral is same for continuous functions as a complex measure, then the measure is same because they give the linear functional, and as linear functional they are same. The complex measure is, if you have any complex measure, that can be written uniquely as linear combination of positive measures. Okay, So the linear functionals given by the complex measure is same, then the measure has to be same. I'm sorry, are you all following? If you have any doubt, you tell me, because I'm talking to myself most of the time. Anyway, I will do this next class. It's 6:30 now, but if you have doubt, you can ask me. I will prove the uniqueness and then how to get this measure mean. Both are very simple, but I will see. Maybe I'm over explaining sometime because I don't see you people, or I don't know, some of you are lost or something. So you have to interact. So tell me whether it is okay. If you don't have any problem, I will stop now.
So can we ask the doubts before next class?
Yeah, before next class, we will discuss this. Okay. Then I will talk about the
Yeah.
uniqueness also, define it clearly, and then we'll talk about the mission. Okay.
Yes, sir. Yeah. Thank you.